So today I'll be going over the chemistry tools in CONVERGE 3.0. We'll go over each of the tools that we have briefly, just to give you a sense of feel what we have in CONVERGE 3.0. Before that, we'll show you some of the results that we have generated with CONVERGE CFD, to give you a feel what our software is all about. So shown in the animation behind in the screen is the result of Flamespeed LES simulation performed by my coworker Chee. Here you can see the flame is highly turbulent, and then there is burning of non-premixed jet. You can see we are resolving on most of the turbulence, and then there is a interaction between the flame and the turbulence. So these are really highly detailed simulation. We also have another example here of CONVERGE usage. This is a ignition in a gas turbine-like condition. We have 5 gas turbine swirler cup, and we have an ignition kernel right around the second cup. And then from this animation, you can see the flame kernel establish itself at the second swirler cup, and then slowly propagating from this second cup to the rest of the 5 cups, and then you're fully igniting a combustion chamber. And this case is done by my coworker Scott Drennan in the Texas office. You can let it go and see that it's quite a lot of intricate turbulent combustion going on in this configuration. And then the last cup would be ignited right about now. This is the complete simulation. So we'll give over. So those simulations that you've seen just now, they are similar with our detailed chemistry solver Sage. And to use Sage, you usually need to give a detailed chemistry mechanism to use it. And so what is a chemistry mechanism or chemical mechanism? To have a CONVERGE use a chemical mechanism, you have to give it in ChemChem2 format. And in this format, there are 3 files that you need to provide CONVERGE to run the case. So first one is the mech.dat. It basically contains a series of chemical mechanism reactions that form a chemical kinetics model of the field that you try to simulate. So in this mech.dat file, we also have a list of species as well as a list of elements. And then we have term.dat, which contains all the thermodynamic properties of the species that you have in mech.dat. And it's in the NASA 7 format. And if you are using species diffusion model, then you need to provide transport.dat as well. This contains the transport property of the species. So the best practice to run a Sage simulation is actually test the mechanism that you're using before using it. This is a really good practice, but usually not done in real life. But the reason we have seen cases where the chemistry mechanism has some changes or bug fixes after it has been published, so there might be some slight differences than what is published if you're getting a published mechanism. Okay, next slide. So how do we evaluate performance of a chemistry mechanism? So the usual way is actually do it through running the simulation of the chemistry mechanism in 0D 1D reactor. The reason being because for these reactors, they're computationally cheaper than running a 3D simulation. So 0D reactor typically means a homogeneous chemically reacting system that only evolves in time. You can think of it as a single cell CFD, combustion CFD. I have an animation of a single cell CFD here in the left. Here you can see it's basically a single box, and then everything just evolves in in time, and there's no inhomogeneity in space. 1D reactor is similar to the 0D reactor, but then now we have it in one spatial dimension. There's only one dimension. You can think of 1D CFD. Shown on the left here, we have a result with 3D propagating premixed flame, and the temperature is a function of distance, exo distance. So all these 0D 1D reactor, we have these bundled with CONVERGE. They are part of chemistry tools. And then these 2 chemistry tools are included with every license of CONVERGE. So if you have CONVERGE, you have access to these reactors. And next slide. So we'll give an overview of what are the tools that we have. As I say, we have the 0D reactor. And all the 0D reactor we have in CONVERGE, they are parallelized. If you have multiple cases, the cases will run in parallel. We have constant volume, we have constant pressure, constant temperature. We also have constant temperature and pressure and constant enthalpy and pressure equilibrium solver. The new feature that we added in 3.0 are the variable volume with heat loss, Reactor reactor, engine reactor, and plug flow reactor. For 1D reactors, they're also parallelized, and we only have one 1D reactor right now, which is the freely propagating premixed flame. In addition to the reactors, we also have maximum manipulation tool. Right now, only reduction is parallelized. So for the maximum manipulation tool, typically we want to use them if you have some issues with your maximum that you're not happy with performance, or there's some cleanup issue. So we have maximum reduction, maximum merging, maximum tuning. We have a Surrogate Blender, and then we have thermodata cleanup. And we also have table generation tool that uses 0D and 1D reactor to generate table. We have TKI table, TLF table, and FGM table. TKI table is the ignition table, and then TLF is the Laminar Flamespeed table. And FGM table is the table for the FGM model. So we'll go over the 0D reactor first. So what the first reactor we'll go over is a constant volume closed 0D reactor. This is probably the simplest reactor one could come up with that is chemically reactant. So it's closed and homogeneous. That's why it's 0D, because all the mixture is not spatially distributed, and it's closed. There's no inflow or outflow, and it's constant volume. The volume doesn't changes, and then there's no heat loss. And to use this reactor, what you give it initial condition, which is a homogeneous mixture, and then if there's reaction, there will be reaction in this closed box. And we have a animation of what kind of a really pictorial description of what a 0D reactor is. You can see it things just react in the box, and everything is well stirred at the same time. The constant volume closed 0D reactor uses the same chemistry solver as our SAGE solver, which is our detail solver. And because we use the same chemistry solver core, you can test maximum compatibility without running the full 3D case. If you have any issue, you can find out right now, because 0D cases are a lot easier to set up. And our constant volume reactor is designed to compute ignition delay. So once you're done running it, we'll spit out ignition delay for each of the cases you give us. And for those who does not know what ignition delay is the time it takes for a mixture to ignite or combust. And like I said, our reactors are parallelized. So the way we parallelize that is that we evenly distribute all the cases to all processors that you have. Suppose you have 10 cases and you have 2 processors. So each processor gives 50 cases and 50 cases. It might not be ideal if some of the cases take something longer than solve. You might have one core finish all the cases, and then the others still working on its cases. So your runtime might be longer than what it could have been. Shown here is also some ignition delay time data that you can compare with experiments. So for those who does not know our SAGE model, I'll give a brief overview here. It's a detailed chemistry solver in Converge. If you're not familiar with Converge CFD, the 3D CFD, we split chemistry and transport together in 2 parts. So first we integrate the detailed chemistry in time to compute the species and energy source term, and then we take those source term and feed into the transport equation. We use the C-Volt solver from the sundials to integrate the chemistry in time. The default option is to use a dense solver that come pre-included in the C-Volt solver. So we also have a earlier solver option that uses a preconditioner with Krylov subspace solver that is also available in C-Volts. It scales better for larger mechanisms that have more than 100 species. Together with SAGE, you can use the adaptive zone. What adaptive zone does is accelerate runtime of SAGE by zoning cells that have similar properties, and we only solve SAGE on the zone, not at the actual cell. So as a result of that, it speeds up SAGE really fast, like blazing fast. You can get up to 100 times speed up in a premixed gasoline cases. So after that detail, we'll come back to the constant volume closed 0D reactor. To this feature, we have made several improvements in 3.0. Now in 3.0 Converge, you can adjust the lower heating value. This is the same feature that we had available in 3.0 since 2.4. And we also have better output control for user usability. Now we have option just to output field cases to one file. So previously, some of our clients to check if there's any fail cases, they'll look through the screen out, which also have succeeded cases and failed cases. They have to sift through that, which is a bit annoying. But now you can just look at one file and then you can see if there's any cases that have failed. Now we also have an option to write out solution every time step. Previously, we only write out solution. We throttle the writing of the solution because we don't write out every single time step. We have some criteria. If it's met, we just write out solution. So we do that because the file could get really huge. But now we have this option. Just if you really want everything, you can get everything. Now we also implement a wall clock time limit. So if you enable this option, we will stop a case if the runtime exceeded certain the runtime for a case exceeded a limit. So you can let's say you have 100 case, you put wall clock time limit to be 10 minutes. So the total runtime will not exceed 10,000 minutes. 10,000 minutes. So then this is really useful for clients who run cases in cluster. So sometimes cluster you need tell the job script on how long a case takes. So in 3.0 we also allow user to have custom mechanism and thermodynamic file names. This is very useful if you're dealing different chemical mechanism and you want them to have different names so that you know what cases you're running using which mechanism. So this is a runtime comparison of our 0D constant volume reactor with an open source solution that's known as Conterra. We are testing it in a different, the same mechanism, that gasoline mechanism by Mel, and its reduced version. So basically what we do is that we take the original mechanism that has about 1,400 species and about 6,000 reactions, and its reduced version that's also available on the internet. I think the reduced version is 600 species and 300 species respectively. And then we run them at the same condition, like eight constant volume cases at 40 bar, 800K and 1200K. The equivalence ratio varies from 0.5 to 2.0. And then the fuel mixture is a mix of 60% isooctane, 30% toluene, and 10% heptane. So run them to these conditions, and then we just plotted the runtime for our solver as well as Conterra. For the Converge, we are running as serial. We are using the ERDIF solver because it's a relatively large mechanism, and we are comparing single core run. So if you can see here, the Converge result, the scaling as a runtime scaling as a function of number of species, we are scaling in between linear and quadratic, versus the Conterra is scaling at between quadratic and cubic. So we are slightly faster than Conterra in terms of runtime as a function of size of the mechanism. And for the tabulated kinetic, for the table generation, we actually use the 0D reactor to generate a 0D constant pressure reactor to generate a TKI table. So the TKI table is tabular kinetic ignition table. This is used by ECFM to predict auto ignition delay. So previously in 2.4, the generation of a table was done through a script or data factory. So we got feedback from client that the script was only serial and it's difficult to use. And for the cloud data factory, some of the client was hesitant uploading the proprietary mechanism over the cloud, and they couldn't generate a TKI table. So now we have heard the feedback. We have integrated this TKI table generate procedure into the 3.0 chemistry tool. So as I say, we generate a table by collecting the result of 0D constant pressure reactor. Now, because we have integrated and supported by Studio, all the setup is going through Studio, and then once you've done the setup, just have the output file and run Converge as usual. For this table generation, we use a slightly more efficient parallelization method than we did for the other 0D reactors. And when it's done, we'll write out the TKI table as the founding of TKI underscore table H5. So you can use it for your ECFM simulation. So what do I mean by more efficient parallelization for the TKI table generation? So for TKI table generation, we use a manager workers approach, where we take one of the core and we tell them, like, this task is the manager task. So what it does is delegate cases to other cores that are the workers' cores. So there's the overhead because we're basically taking one core and telling him, you're not solving more cases. Your job is to delegate tasks. You don't do solution. So each of the worker they will get the next case from the manager, and then once they finish the current one, and then they will get another case from the manager until all the cases have been finished. So in addition to delegation, the manager call also writes out result to the disk. This is really nice for our TKI table because we are writing out a TKI table, and if you have many cases writing to the same file at the same time, it could create some issue for certain file system. This parallelization strategy scales better than the naive one, where you just distribute equal cases to everybody if there are outlier in your cases. So usually in the TKI table, you have edge cases in the corner cases, because usually TKI table spans a wide range of conditions, and that could slow down your simulation. If you have small amount of core, the overhead can be large, but when you're generating table, usually you want to put as many cores as you could within your allocation, and just get the table generated as fast as possible. You can see the speed up, the comparison between the naive method and the manager workers method, and the ideal scaling as a function of number of core. So if you have 10 times the core, you should see 10 times the speed up. And then if you can see the manager workers actually follow closely the ideal scaling, but with some overhead because we are sacrificing one core. And for the naive approach, there are some drop-off compared to the ideal scaling. So this is a test using our reactor. So that's why we make this available to the TKI table. So this is a new feature that we have included in CONVERGE 3.0, which is the variable volume and heat loss. It's basically the constant volume, 0D homogeneous reactor, but now we let the volume change. The user has to specify the volume of the closed homogeneous reactor as a function of time. So the reactor is still closed, there's no inflow outflow, it's just the volume is allowed to expand. And then now you can also prescribe a heat loss term. There are two options here. You can just set a Q dot term, which is a heat loss per unit of time, or you can use a wall heat loss model, which the user provide wall heat temperature, surface area, and heat transfer coefficient will create the heat loss based on these the equation. So this is another pictorial description what is happening. This is a compression case, the volume is changing, we also have heat loss at the same time. So combining these two features, you can use it to model a rapid compression machine. In addition, you can also use it to model a homogeneous charge compression ignition engine. So for those who do not know what a HCCI engine is basically a premixed engine without spark, but you also run at a higher compression ratio. This is a really simplified model. In real life, there might be inhomogeneity, but this is a simplified description. So what this does is leverages the variable volume feature that we added. So instead of user-provided volume, we use an equation to describe the engine volume as a function of crank angle. I think we use a textbook equation from Hayward for this. From that equation, you obviously need to specify some of the engine geometry parameters like bore, stroke, connecting rod, crank offset, RPM, compression ratio. We also have a heat transfer model. You can have adiabatic model, which is basically turning off heat transfer. You have heat transfer coefficient profile as a function of crank angle that you have to specify, or you can use some of the textbook or 0D engine heat release model that are also available with this feature. So the output of this feature is that it will output the crank angle if there's ignition. It will output the crank angle where ignition starts to happen. So originally this feature was used internally we originally have this feature to give a quick estimate of the octane numbers of a particular fuel, but then we also make it available as just a standalone feature. So here we have an animation of what a HCCI engine kind of looks like. There's no spark, we just have a volume that is contracting and expanding, and then it will ignite at the top dead center, supposedly. So brief overview, what are the octane numbers? So we have research octane number and motor octane number. If you're in a gas fuel pump, usually there is a octane number, which is the average of these two. RON and MON, they are the abbreviation. These are the measure of knock propensity of a fuel. And to get a RON and MON number of a particular fuel sample, what we do is that we use there's a standardized testing method to get the RON MON, and we use a research engine from CFR. It's a spark ignition engine, and you run that with different compression ratio until you can get knocking of the fuel. So based on how the fuel sample knock, they are compared against PIF fuel to determine its Ron and Mon value. And the actual procedures in the standards is just a really brief overview what it is. So, and in case you don't know what PIF fuel is, it's basically a blend of isooctane and N-heptane. By definition of Ron-Mon, the way it's defined, isooctane has a Ron-Mon value of 100 and N-heptane has a Ron-Mon value of 0. There are Ron-Mon value of greater or negative or greater 100 and negative, but we won't go into here. This is just a brief overview for those who are not familiar with Ron-Mon. On the left here, we have a table of the Ron-Mon engine parameters. So Ron is running at 608 RPM, Mon is running at 900 RPM, and the inlet air temperature for Ron is 52 Celsius, and the Mon is a bit lower at 38 Celsius. The inlet temperature, mixture temperature is not specified for the Ron, but for the Mon, it is specified at 149 Celsius. The spark timing for Ron is fixed at 13 degrees before top depth center. For the Mon testing, you can vary it between 9 to 26 before top depth center. So there are some differences. I think the Mon is a bit more, that you can control knocking a bit more better. Okay, so now we have the HCCI engine, and so we're using it to estimate Ron-Mon. So what we're essentially doing is using an HCCI engine that has analogous to the CFR-SI engine. We use the same engine parameter operating condition, but we just don't have the spark. Similar as the CFR engine, we have variable compression ratio. We change the compression ratio of the HCCI engine. So what we do is that you give me a fuel sample, a fuel mixture, and then what we'll do, we'll take the stoichiometric mixture, put in the HCCI engine that we have that matches the CFR engine, and then we systematically change the compression ratio until we find a critical compression ratio where the mixture can ignite. And then once you have the critical compression ratio for that mixture, and then we'll look up from a calibration curve that are constructed with a PRF fuel. The default calibration curve that we use is computed using the law and Zilmore PRF mechanism. So we believe this is a kind of estimation of Ron-Mon, even though it's not an actual Ron-Mon engine, so it gives us some kind of good correlation between the Ron-Mon. We also have an option that you can use a user-generated calibration curve and then use it in this mode. Obviously, you need to generate a calibration curve with a mechanism that has the PRF component, which are the isooctane and heptane, and then you can use it instead of our default calibration curve. So another new feature that we have added is the Wellster reactor. So for this reactor, it's no longer closed. We have inflow and outflow now. It's a constant pressure 0D reactor. You have inflow. The inflow is assumed to be, the outflow is assumed to be the same as what is inside the reactor, and the reactor is really well mixed. That's mixed at 0D instead of more complicated. So because we have inflow and outflow, now the user needs to specify reactor size as well as the inflow properties. This model, we can also couple heat loss model, and we also add the option to ignore energy equation. Basically, you make this a Wellster reactor, a constant pressure and constant temperature 0D reactor. So this reactor, people usually want a steady state solution, and the way we achieve that is by time stepping until the solution stops changing. So the usage for this Wellster reactor, we can find the extinction and ignition limit as a function of resident time. Resident time is kind of indicator of the mass flow rate. And then you can also couple this with surface chemistry, analyze species conversion in a Wellster reactor. And sometimes this is also used as a simplified model of combustion in a gas turbine engine. You can see left here, you have a Wellster reactor right smack in the middle of the gas turbine combustor to model the flame. So another feature that we added in 0D reactors, technically not a 0D reactor, but we put it as a 0D reactor because the way we solve it is a plug flow reactor. It's essentially a pipe flow that only varies in only changes in the axial direction. So axial convection and chemistry are the only two dominant physical processes that we consider in this model. So because it's a pipe flow, users need to give domain length and cross section as well as inlet velocity. So just a brief overview why we consider it as a 0D reactor, because the way we solve it, we use the matching method. So what we do, we start from the inflow end of the domain, and then we solve a constant pressure ODE reactor from this inflow to the end of the domain of outflow. So what we essentially do is take the 0D constant pressure reactor, we run it with slight modification so that we can convert the time into a spatial dimension. So once you're done running this reactor, you can use the result to compare with speciation data from a flow reactor experiment, which is basically experimental analog of a plug flow reactor. As of 3.0, we don't have variable cross-section yet because how we do the solution method, and we'll probably change it in the future. So we'll go over the 1D reactor right now. So for the 1D reactor, we only have the 1D freely propagating premixed flame. So it's just a brief introduction what a 1D freely propagating premixed flame is. Basically a planar flame propagating the homogeneous unburned mixture. You have this illustration of what it is. So you have a flame, you have burnt mixture, and it keeps moving into the consuming unburned mixture. So this is a really simple theoretical geometry which people solve to get the Laminar premixed flame. The solution approach that we do is that instead of letting the flame freely propagating, we impose an inflow so that we fix the flame. So this approach is easier for more tractable to solve. So as I say, the primary output solving this 1D reactor is to get the Laminar premixed flame, which has many use. We have for this 1D premix model, we have user can use a mixture average species diffusion, which means I mentioned earlier you need to provide a transport data if you want to use mixture average species diffusion in this configuration. To solve this problem, we have a variety of strategy available in Converge. We have the Newton steady state solver, which is the classic, which is really fast, but then for those who have used Newton solver, it can diverge if you give it really bad initial condition. We have now approach where you can use Converge CFD piece. Basically, we use the 3D solver by running it in 1D mode. It's a lot more robust, but then because our 3D CFD solver is transient in nature, you have to be careful with your time step size. If you take too big time step size, you might run really fast, but you might miss out on some of the accuracy. And the third approach is basically combining the previous two approaches. What we do is that we first use our 3D piezo solver to get an initial guess, and then we feed the initial guess into our steady state solver. Okay, so we have improvement. We have some improvement done to the 1D freely propagating premixed flame solver. We have the same usability from the 0D reactor. Now we have adjustable lower heating value, better output control, wall clock time limit, and then you can have custom file names for maximum and as well as term. Now we also have equal species diffusivity support in Newton solver. It was previously only available in the piezo solver in 2.4. To use this option, instead of giving a transport.dat, or you give the solver the guess.dat. We also take the parallelization method that we use in the TCAD table generation. We use a one manager and workers method that I described earlier. We also have a sparse solver available for bigger maximum. We'll go over that later. And then we have an anchor temperature that is used by the Newton solver to anchor the flame. We can make that value automatic now. And so previously in 2.4, user had to specify a one value, and then that value might not be valid in a wide range of conditions for one that might encounter if he or she is generating the Laminar Flamespeed table. Again, I'm showing here again the 1D premix solution. The temperature is it's a function of a space. So the sparse solver, is only available and it's only needed by Newton, because in the Newton solver we need to construct a Jacobian matrix and solving it. That's how the Newton solver works. And then the old approach to construct a matrix, usually if you have a mixture average species diffusion turned on, we use a correction velocity to keep the species sum up to species mass fraction sum up to 1. But the issue of this is that it creates a dense banded matrix. Shown on the left here, you can see is a banded matrix, but then each of the banded matrix band is really dense. And the matrix is constructed through finite difference, so that's quite slow. So the newer approach is that instead of using correction velocity, we use nitrogen as a dilution species. So we don't transfer nitrogen. We just use a nitrogen, absorb the error, so to ensure the species mass fraction sum up to 1. So what this do is that result a greater sparsity on the matrix. So you can see left here, after we use a new approach, we still have a dense matrix in the diagonal, but the sub-diagonal matrix, we are more sparse now. So to solve this matrix, we have a faster runtime. And then in addition to that, we also compute this matrix analytically, so computationally is more efficient. So what is the performance of this sparse approach? So again, we run it against Cantera. We're using the same Gaslin mechanism by Mel et al. And it's a reduced version. In case you remember, the mechanism have about 1,500 species, and the reduced version have about 600 and 300. And this time we're running an ambient condition, 300K and 1 bar and stoichiometric mixture. The few mixtures are the same, 60% by volume isooctane, 30% toluene, and 10% F15. For the Converge, obviously we're using the single core and we're using the sparse solver for the bigger mechanism. And the Cantera, we just use the default option, and it's downloaded from the internet. As you can see, with this sparse matrix approach, Converge in the blue line is scaling in between quadratic and cubic. And then versus Cantera, the scaling is more than cubic, and it's probably too impractical to run Cantera for this kind of mechanism of this size. So obviously the sparse solver requires you to have nitrogen in your system, which should be correct for most of the use cases. We compare the result for the same case, but now we are changing the equivalence ratio. These are result comparison. We are plotting laminar Flamespeed in terms of equivalence ratio. As you can see, the Cantera is in orange and Converge is in blue. The results are more or less on top of each other for most of the conditions. And I think these are sufficient for generating a Flamespeed table. So now we move on to the Tabular laminar Flamespeed table. So this table basically tabulates laminar Flamespeed in terms of unburnt temperature, pressure, equivalence ratio, EGI, and fuel fraction. So this table can be used by premixed combustion model that need laminar Flamespeed as a part of the model input. So they're usable by G equation, ECFM, FGM, TFM. So in the example of TFM, there might be additional variable that we need in the table, and our Converge 0D table generation can do that also. So we can add additional variable in the table if your model desire it. We also have a utility to convert the table for visualization. So shown on the left here is it's a visualization of the table I've generated. There are isosurface of Flamespeed, and then I also did some cut along the pressure plane to give you a trend how a table usually look like. For now, the table generation only uses the Newton solver. It does not support the piso or the hybrid solver yet. But I believe with the sparse solver, the Newton solver is really fast, so that's why we have that option for Newton for now. Okay, so we'll go over the mechanism manipulation tool. First, we'll go over the reduction tools that we have. So the goal of the mechanism reduction is to optimize the sign mechanism for the set of condition of interest. So example, if you're running only high temperature cases, it could technically remove the low temperature chemistry. So the operating principle that we use a graph theory method to systematically remove species, while ensuring you have a set of cases that a 0D 1D case that you give us, make sure the error for those cases are within certain tolerances. So the improvement over 3.0, over 2.4 and 3.0, we have added 1D freely propagating cases when you do mechanism reduction. So basically we are checking the error in laminar Flamespeed during reduction. Previously, you only have ignition delay cases, and so we have improved it. Although not encouraged, if you're not happy with the size of mechanism from your first reduction, you can run it over and over again. But then the issue with that is that the errors are cumulative, so you end up you might get a mechanism size that you want, but then the error might be too large to make it of any use. So to that, we have a mechanism tuning tool that you can, if you over reduce your mechanism, you can kind of use it to correct the mechanism so that it's back to the original mechanism performance. So what it does is tunes the most sensitive reaction based on the cases you give it. So you give 1D cases, and then it'll run the sensitivity analysis and find out what are the most sensitive reactions. So tune the pre-exponent factor of those reactions. And to do the tuning, we use our Congo tool, which is also included in Converge. This is a genetic algorithm optimizer to optimize the reaction coefficient so that we can best match ignition delay as well as lambda flame speed. For example, here we have a CSI 931 mechanism that we reduced once from the Lons-Lemore diesel surrogate mechanism. And then we have a really small mechanism that we further reduced that has 83 species that we call it the CSI 83. It's overly reduced by any standard. We don't encourage it. But then, so if you plot the result of ignition delay of Sandia spray bomb, those listed condition, you can see the red is the baseline results, and then the blue is the overly reduced mechanism CSI 83. So what we did is that we ran it through the mechanism tuner to tune it and give it target of the original mechanism, and then you can see the green curve, which is the performance of the tune mechanism. You can get it recovers some of the ignition delay time that are closer to the original baseline mechanism. For the next tool that we already have in Converge is the Surrogate Blender. As you know, real gasoline fuel or diesel fuel are complex mixture of thousands of component species, so it's really complicated. So the approach is that use like probably handful of fuel surrogates to model the real fuel, to simulate the real fuel. You still multiple component, but the component is way less right now. You can count it. So what this tool is create a final surrogate mixture that can best satisfy certain properties that are target imposed by the user. So example here, but there's restriction for this tool right now. The physical property needs to be governed by simple mixing law because the blender right now it's linear in its algorithm. The approach is linear. So we have an example here in the left in the Surrogate Blender tool in Studio. You give it 4 fuel and then a couple of DCN derived cetane number target and the Soothing number index and the HC ratio as well as the molecular weight and target and the weighting you wanted them, and then you click the blend, it will spit out the mixture of fuel 1 to 4 that best satisfy these targets. So the next tool that I'll go over is the mechanism merger. So what it does is merge 2 mechanisms together. One may ask, why do you need to do that? So there are 2 instances that we have found out why one would want to do this is that we want to merge a chemistry mechanism to a main chemistry mechanism. So let's say you have NOx, you're merging to a main mechanism, and you can merge 2 mechanisms from 2 different fuels to make one big mechanism that can handle the 2 different fuels. So what this tool is a help of species and reaction conflicts. So when you have 2 mechanisms, you have species that could have the same name but different thermodynamic properties or reaction that are the same. And you want to keep all of them, or you want to just take one over the other. So for example, here we have done a merging of 2 Lons-Lemore mechanisms, isooctane and heptane. We call it the CSI merge. And then we have just the Lons-Lemore PRF mechanism, Lons-Lemore gasoline mechanism. So we ran the merge mechanism as a gasoline as well PRF mechanism for a PRF 980 mixture at the 40 bar and stoichiometric. Oops, sorry. And then you can see the merge mechanism actually follows closely the gasoline mechanism, and then it's like it does pretty well for a really simple merging job. So, but do be careful. You want to test your merge mechanism after you're done merging them, because if you didn't do a good job, you might get results that are way off cuff. The last tool I'll go over is the thermodynamic data cleanup tool. What it does is remove unnecessary and duplicated species in term.dat, and then it only keeps the species that you have in mech.dat. It's really useful if you found out your term.dat is still really big after mechanism reduction. So when you run this tool once, you can get a smaller term.dat that is more befitting than for your reduced mechanism. Sometimes you can also fix term.dat by removing species not in mech.dat, because some of those unused species may have malformed data that can cause this issue. So, but that's not guaranteed. Like sometimes it works, sometimes it does not work. So in summary, compared to open source offering, we have a 0D, 1D chemistry solvers that are faster and they're better integrated with our CFD tools as well as Studio. We use the same format. You can just take the file and run run one after the other. In 3.0, the chemistry tool have received significant upgrade in feature. We literally have double number of 0D reactor types. For the existing feature, we also have improved it. Now we have added table generation support, and we have added some output control that to give it better usability. And a lot of these come from our user feedback. We like why we added certain improvement to the usability. We do appreciate. If you do have any feedback, let us know if you have when you're using these two. So the availability of these chemistry tools, some of the tools are already available in 2.4. They are non-bolded. To remind you what are tools that are non-bolded, we have 0D reactor, we have constant pressure, constant volume, constant temperature, and the HP and TP equilibrium. And the new feature that are only available in 3.0 are the variable volume, repeat loss, HCCI Engine, valve reactor, plug flow reactor. For the rest, 1D and 1D reactor maximum manipulation tool, they're all of them already available in 2.4. For table generation, the TKI and the TLF table are the new feature in 3.0, and the FGM table is already existing in 2.4. For all these tools, they will be available in Windows and Linux platform. They come pre-packaged with the Converge license that you have. If you're currently not a Converge user and want to try out these chemistry tools, please contact info@convergecfd.com for follow-up. We'll hook you up if possible. And thank you for attending this webinar. My email is shown here. And then if you have more general email question that are not related to chemistry tool, you can go through the info@convergecfd address.